Well, welcome back. We are in our ninth topics. Okay, this topic would be on Thevenin's theorem. Okay, Thevenin's theorem. So, Thevenin's theorem is simply another method, okay, to simplify your circuit. You have a very complicated circuit. For example, if you have maybe a circuit that look like this, no, something like this, right? Many R's, maybe many sources also, okay? And this is terminal AB, okay? You can use Thevenin theorem to simplify this whole thing here, okay? Represented with only two elements. The voltage source, we call it Thevenin voltage, and in series to that VTH is Thevenin equivalent resistance, okay, RTH. Okay, so you can see that these points stay the same, right? This terminal AB. You replace this whole complicated circuit with only these two elements, which would make your life easier. Okay, so the definition of VTH or Thevenin voltage is that VThevenin is the open circuit voltage between 2 points in a circuit. Okay, it could, what it means is that, well, if some problem, it may ask you that, okay, I want to know what my Thevenin right here, circuit right here, looking from this point of view, okay, from this R in, this resistor. Okay, so it could be a different point in a circuit that the question can ask you. Okay, so RTH, Thevenin equivalent resistance is a total resistance appearing between two terminals with all the sources placed by their internal resistance, which means that all voltage sources are shorted and current sources are open. So pretty much it means that you look into the terminal that you are asked to find Thevenin equivalent circuit, and you short all the voltage sources and open all the current sources and find R total, and that will become your R Thevenin. Okay, so that's the simplest way. So therefore, first, let's say that if I have to find RTH having only independent sources. Okay, so therefore, let's see, is there any example? Right here. Okay, this is an example. Please find Thevenin equivalent circuit between point A and point B. So terminal AB. We want to find that. Okay, well, but it's already given as an open circuit. See, it's open. The terminal is open. So first, okay, let's find VTH, right? VTH. So VTH is simply the voltage that you can measure if you put the probe at point A and point B. Okay, point A and point B. Okay, so therefore, let's see what VTH is in this case. Well, the current, right? Current is a key element, okay, of your circuit analysis. You should know where currents go, where the voltage appears. Okay, so in this case, where current come out from the source, okay, right, IS, okay, goes through here, right, come to this junction. There's two branches, okay, R3 and R2. Well, but R3, it's open circuit right here. It's not a complete path, so the current does not go through to R3. So therefore, it all flows here and goes here. Okay, as the current flows, of course, there's a voltage drop right here, right, V1, and this V2, right, VR2, V2. Well, as the current does not go into R3, so therefore there is no voltage drop across here, so 0 volt across R3, right, because there's no current flowing through it. So therefore, if you want to measure the voltage at point A and point B, well, if this is 0, right, then that means that the voltage here, this would act like you can imagine it as like as a wire, right? Then this point here is the same as this point here, okay, and this point B, of course, is the same as this point here. So therefore, from this configuration, you should be able to see it that VTH is nothing but V drop across R2, which is V2. Okay, it comes to R2. So that's your job. What's V2 then? Well, V2 is in a loop, Okay, and V2 is, if you write down KVL, right, you have Vs equal to V1 plus V2, the KVL, right, for this current Is, okay, for this loop. Well, you can see that V2 is part of Vs, V1 is also part of Vs. So V2 divided from Vs, so we can use voltage dividers. Okay, you can use voltage dividers. So the formula for voltage divider is Vx equal to Rx over R total times Vs. Okay, well, therefore V2 would be equal to, well, Rx would be R2, right, divided by R total. Vs, well, V2 came out of Vs, so this is still Vs. Okay, R total is the total resistance that Vs has to give to, divided into which R's. So in this case, it divided into R1 and R2, and they are connected in parallel. So therefore, in series. R1 connected in series with R2, so R1 plus R2. So this is your answer for VTH. Okay, equal to V2. Okay, so now what about RTH? How do you find RTH? Okay, well, you look into the terminals, right, with all the sources turned off. So if a voltage source, you short it. So you short it and you look into the terminal, what is R total? Okay, so imagine R total. Imagine the current goes here, boop, boop, in here, right? Divide into these two. So R1 and R2 connect in parallel. So R1 parallel R2, right? And then in series with R3. So it's like this. R1 parallel R2, R3, right? AB, looking in there. So R3 in series with R1 parallel R2. So it becomes R1 times R2 over R1 plus R2 times plus R3. This is your R total. So you get your RTH. So RTH equal to R total. So therefore, your Thevenin equivalent circuit would look like this, right? So this is your VTH, right? R2 over R1 plus R2 times Vs, and this is your RTH, and this is the terminal AB. Okay, so this is Thevenin equivalent circuit. Okay, now let's look at this example just to show that you can find Thevenin equivalent circuit at different terminals in the circuit. So the first case was I want to find at Thevenin equivalent circuit at terminal AB. So if you let's say I'm going to do the first one, right? R1, R2, A, B, R3. So this is your circuit, Vs. Okay, right? So to find VTH, well, current flows here, flows, go through R1, go through R2, go through R3. Yeah, it's another one loop. If you run down KVL, it will be Vs equal to, well, if you have this plus minus V1, right, plus minus V2 plus minus V3, V1 plus V2 plus V3. So it means that V1, V2, and V3 are divided out from Vs. So I can use voltage divider. So therefore, the voltage drop across, right, this would be VTH for VAB. So therefore, it will be the voltage drop across R2. So therefore, using voltage divider, right, it would be R2 over R total, right, R1 plus R2 plus R3 times Vs. Okay, so this is it, right, here. What about RTH, right, RTH, oh, sorry, let me redraw it again. Okay, so RTH, I have to short voltage source, right? See, I forgot to short it. So short your voltage source. So R1, R2, and R3, AB. So look into here, what's R total? So if you imagine that there's current flow, it go like this, right? It come up from A like this, it go like this, and spin to like this, right? Come here, come here, come here, come here, right? Okay, and they all go back into here. So if you see that, well, the current that go through R1, same current go through R3 also. So that means R1 and R3 is in series. R1 and R3 is in series. Okay, and see that this one, right, R2, this node here, right, node A, this is node B, it's connected in parallel with R1 plus R3. Okay, see that? So it's like, if you have this A, right, A, B, this is R2, right, connected with A is R1, and R3, and the other node R3 connected to point B. So therefore, there are R1 plus R3 in parallel with R2. So this is the case. Okay, so this at terminal AB. Now next one, terminal BC. Terminal BC. You can try to do it before looking at, pause my lecture right here, right, and try to do it yourself, right? So for BC point of view, right, so the voltage across for BC would be voltage drop across R3. Okay, so it would be R3 using voltage dividers rules, R3 over R total, which is R1 plus R2 plus R3 times Vs. Okay, so for RTH, right, if you imagine that you shot this, right, you shot this picture, okay, and imagine that where you have a current coming here out of B here, it will split into this one and this one right here, split into R2, where the same current go through R2 and R1, so that means R2 and R1 is in series, right? Okay, then of course point A and point B, it doesn't split, it come together right here, so therefore R3, R total is R3 parallel with R1 plus R2, right here. So this is RTH. Okay, and you can try to figure out, understand. Okay, you get this correct for AC, terminal AC. Okay, so this example is to show you that there are different answers. Okay, for if you look at different terminals of the circuit. Okay, your VTH and your RTH is different. Okay, well, this is when you have independent sources in the picture. Okay, in the circuit, but then to find RTH, there are other ways also. I will go real fast. Okay, your RTH actually, the general form, okay, is RTH will be equal to V open circuit. Okay, V open circuit over I short circuit. OC stand for open circuit. SC stand for short circuit. Okay. So in this case, it doesn't matter, okay, if you have a dependent or independent sources or only dependent source even. Okay, so to find Thevenin resistance for circuit with one or more dependent sources, we cannot simply we do not set dependent source to become zero, but we have to find it through this formula. Okay, so what it mean by VOC and ISC? So if you look at this circuit, okay, look at these circuits. We want to find the Thevenin equivalent circuit looking through terminal AB right here. Okay, AB right here. So this will be our VTH, which is our V open circuit at terminal AB. Okay, right? So therefore, you look at it and go, oh, but then it's simply V drop across 6 ohms. V drop across 6 ohm. Okay, it's already V drop across 6 ohms. So this is become your VTH also. Because there's no current going through these 10 ohms, so therefore no voltage drops, 0 volt. So the voltage drop at AB is the same as the voltage drop at 6 ohms. Okay, so therefore you see, okay, the current come out from the 20 volt, go here. Oh, okay, then it's only one loop. So let's try to count KVL. So KVL, if you see that we also have dependent source here, 2I. Please don't mistake that it's current source because you see I here. Okay. See I here, it's actually voltage source because there's a positive and negative sign there, right? So this is I, the current I here, they're flowing, right? I is here. So therefore, going through with it, so you see 6 I's, the voltage drop across 6 ohm is 6 I's. Oh, you see where they start walking from here. So you see minus 20 plus 6I right? This one right here, sorry, see a minus sign right here first. There's a minus sign right there. So therefore minus 2I, and then plus 6I again. The voltage drop across 6 ohm. So therefore I is equal to 2 amps. And then that means your VOB, your VTH, right? Your VTH is the voltage drop across 6 ohm is 6 ohms times I, which is 2 amps, so 12 volt. So you have 12 volt. Okay, this is your open circuit voltage, right? We want to find RTH equal to VOC over ISC. Okay, ISC. So VOC we got now is 12 volt because open circuit, but now we have to find ISC. Short circuit, where is the short circuit portion? It means that you have open terminal AB already, right? So now you short, put a wire between point A and point B, and your current ISC is that current where you shorted the terminal. Okay, so ISC is there. So now you have this circuit. Okay, so in this case we use loop, okay, mesh analysis. Okay, so mesh I1 and mesh I2. Okay, so I is still here. The problem, sorry, that there's supposed to be I right here. Okay, as part of the problems. So that's why there's an I right here. Okay, 6 ohms right there. The problem assigned I there. Okay, so therefore we did KVL from each mesh. So minus 20 plus 6I1, now become I1, minus 2I because there's a minus sign here, right? Plus 6, right? 6 I1 go into positive direction. We are in mesh I1, okay, and I2 go into a negative, equal to 0. You get these equations. The second mesh, okay, for I2, right? I2 KVL loop I2. So I2 goes C6 I2 minus I1 plus 10 I2 equal to 0. So you get these equations. So you use these two equations to find I1 and I2. But the short circuit, as you can see, that it's I2 only, right? Because I2 flow like this and like this. So the same as ISC, I short circuit. So therefore your answer that you want is simply I2. So which is this one. So therefore your ISC is 0.88 amps. And the answer, when you divide it together, it becomes 13.6 ohm. So therefore your Thevenin equivalent circuit consists of the VOC or VTH, which is 12 volt, in series with RTH, which is 13.6, point A and B. So in a way, so you have simplified this circuit with even dependent source, right here, AB, okay, to become simply 12 volt and 13.6 ohms AB. That's it. So it makes your life easier, whatever you want to insert at AB. Okay, you have a 12 volt and 13.6 ohm instead of this like two sources, dependent sources also. Okay, so this is one way, a general way. Okay, so you can see that the problem has both the independent source and dependent source. Okay, the third one, let's see. Okay, the third one is, okay, if you have only dependent source, okay, to find RTH in case there is a dependent source, okay, it can be done, but you have to put in a test source into the problem. Okay, test source into a problem. So therefore, what we do is we apply either the voltage test source V out, and if you do that at the terminal you want to find, you find I, the current going through there, and your RTH is this formula V over I. Okay, or you can insert a current source, whatever values you want, 1 ohm, 1 amp, 2 amp, 3 amps, or V equal to 1 volt. I use 1 because it's easy to remember. Okay, so another one is you can insert a current source, for example 1 amp at the terminal, and then you have to find V out. So you have to calculate VRTH, R Thevenin from V out over I out. Okay, so like this. If you insert V out, test voltage like this, you have to find I out. Okay, if you insert the current source I out, you have to find this V out. Okay, so this is the case. So for example, the problem right here, this problem here, the problem consists of only current control voltage source. Okay, we want to find so-called VTH and RTH for this. Okay, so in this case, I'm going to apply current test source. I'm going to apply 1 amp in there. I apply 1 amp at the terminal. Okay, if I write down, this is AB, so this is AB. Okay, terminal, and then I need to find what V out is. What V out is. Okay, so our job to find V out. Okay. Well, I'm going to use, in this case, use nodal analysis going to find V out, right? V out is right here across this, it's this node and this node, right? Across the current source. So therefore, it's also right here, right? So this is V out, see? So I'm going to use nodal analysis. Well, this is ground, okay? So I3, write down KCL at node V out, okay? So I3 going in, positive I3, I2 is leaving, for is minus I2, right? But we have 1 amps going in. So this is actually 1 amps. Okay, 1 amps going in. So therefore, change it to so-called node voltage, right? Well, I3 for node voltage, I3 is a current passing through 3 ohm. So there must be the voltage drops across 3 ohms right here. Okay, the difference between the potential between this terminal, positive terminal, and the negative terminal. So the positive terminal is this voltage here. This is a current source, right? So therefore it's 1.5 I. So 1.5 I. Okay? Minus V out, because minus whatever this terminal is, which is V out, divided by 3. So this is I3. Okay? I2, current passing through 2 ohm, so it's we drop across 2 ohm is V out, so V out over 2 equal to minus 1. Okay, so therefore you do the math. Okay, so you do the math, and also you get the answer. Also I, right? I, the problem to give I in this is your I, right? So in this case I is, if you have insert 1 amp, so you see that I is equal to minus 1, is in the opposite direction. Okay, so therefore your I here is equal to minus 1. Okay, so therefore you get V out equal to 0.6 volt. Okay, so therefore it's easy as that. So your RTH is equal to V out divided by test current source 1 amp, so it's 0.6 ohm. So your equivalent circuit in this case simply 0.6 ohm. With only current circuit with dependent source, you don't have VTH. Okay, so this is your equivalent circuit for this problem right here. Okay, so this is another way of doing it. Okay, so therefore this is it for Thevenin theorem. Thank you.